Welcome back. The focus of this video and the next one is going to be wireless networks. The contents of this video are medium access control, wireless links, and spread spectrum. When multiple nodes transmit simultaneously on a multi-access link, the transmissions interfere, and that results in the receiver being unable to decode the sent message. And therefore, the access to the physical medium must be regulated. And this is called medium access control, and this is the first topic that we'll discuss. Second, since our main focus will be medium access control in wireless networks, we will review the properties of wireless links. It turns out that wireless links suffer from relatively large bit error rate as compared to guided media, primarily due to interference. Spread spectrum methods help in mitigating the effects of interference. This would be the last topic of this video. By the end of this video, you would know how is medium access control done in multi-access networks, specifically wireless networks, and how are wireless transmissions made resistant to interference. Recall that wireless links communicate by transmitting electromagnetic signals, and therefore wireless links all share the medium, or so to speak, they share the same wire. And the main challenge then is to share this medium efficiently without unduly interfering with each other. At a first glance, this sharing can be accomplished by dividing this wire, so to speak, or the medium along the dimensions of frequency, time, and space. And we are going to discuss protocols that facilitate this sharing in the next slides. The medium access control sublayer is responsible for regulating transmissions on multi-access links. Medium access control sublayer is the lower part of the data link layer. Ethernet, Wi-Fi, and Bluetooth all implement physical layer as well as MAC sublayer functions. There are two kinds of MAC protocols. One is called contention-free MAC protocols, and the other one is called contention-based MAC protocols. Contention-free protocols ensure that when one node is transmitting, no other node interferes with the transmission. The contention-free protocols themselves are of two types, fixed and dynamic. The examples of fixed contention-free MAC protocols are TDMA and FDMA. They stand for time division multiple access and frequency division multiple access. We had discussed time division multiplexing and frequency division multiplexing in an earlier video. In case you are having difficulty in recalling, I suggest you consult that video. But in just briefly, remember that in the case of time division multiplexing, we divide time into discrete slots, and then every node gets one slot or more slots in which this node is going to transmit, and no other node transmits in that slot, and therefore it ensures that the transmissions of this node remain interference free. In the case of frequency division multiplexing, we divide the frequency band into smaller subbands, and then different nodes are allocated individual frequency bands in which they transmit, and that also isolates the transmissions of a node from being interfered by other transmissions. These static allocations are wasteful in the case when the node is not transmitting. Basically, it has the resource, but that resource is not being utilized, and they also tend to increase average delay. The second category of contention-free MAC protocols are dynamic protocols, examples of dynamic contention-free MAC protocols are polling and token-based protocols. In the case of polling, there is a central node that polls nodes in, let's say, round robin order and asks whether they have some message to transmit, and then basically if a node has something to transmit, it transmits. In the case of token-based protocols, there is a token that circulates among the nodes, and a node that has the token has exclusive right to transmit. Once it is done transmitting, it passes the token to the next node in some predetermined order. The second category of MAC protocols is contention-based MAC protocols. In the case of contention-based MAC protocols, nodes compete for channel access. Since multiple nodes may transmit at the same time, collision can occur. There are two contention-based MAC protocols that we will discuss in this video. The first one is called Aloha, and the second one is called CSMA, or stands for Carrier Sense Multiple Access. The protocol Aloha was part of a network called Aloha Net that became functional in 1971. It was developed by Norm Abramson for wirelessly networking the different computers located at separate islands in Hawaii, or all part of University of Hawaii campuses. In Aloha Net, a node transmits a packet whenever it needs to send one, without any regard for whether there is another transmission going on at the same time. And these nodes communicate with a central node, right? And the central node, once it receives packets from a certain number of nodes, it simply rebroadcasts all the packets that it received. Let us suppose this green node is the central node, and these red ones are the nodes that are located at different islands of Hawaii. And so in the first go, these nodes would transmit messages to the central node, and then the central node simply rebroadcasts those messages. So all of these nodes hear what was sent. And so that's how, for example, let's say this node A wants to communicate to B. Then in the first go, it sends this message to the central node. And then once the central node rebroadcasts that message, B gets that message that A had sent. And this also serves the purpose of detection of collisions. So in the rebroadcast sequence, if the node does not hear the message that it had sent before, it infers that that message resulted in collision. The maximum throughput of Aloha is rather low. It's only 18.4%. A person by the name Larry Roberts improved the performance of Aloha by proposing what is known as slotted Aloha in 1973. In slotted Aloha, nodes are restricted to start transmissions only at slot boundaries. And so in slotted Aloha, the time is divided into discrete time slots, and a node is allowed to start transmission only at the start of one of the slots. So here is one example. So we have these stations starting from A to H, and A sends in the first slot, and then in the second slot it's the D that transmits. In the third slots, all of these stations C, F and H transmit at the same time, and so that results in collision, and therefore you can see C transmits in the following slot. So in contrast to slotted Aloha, the original version of Aloha that was developed by Norm Abramson is known as pure Aloha. And slotted Aloha improves the throughput by a factor of 2. So the maximum throughput of slotted Aloha is 36.8%. The slotted Aloha's performance improvement comes at the cost of need for clock synchronization, because we have now this time slot structures. All the nodes in the network need to agree on a common slot boundaries, and that's actually an overhead not just with slotted Aloha but any MAC protocol that relies on time slots. One way to accomplish this is that you designate one node as a coordinator, and that node basically sends periodic beacons, and those beacons act as a clock synchronizer. The next medium access control protocol that we will learn is called Carrier Sense Multiple Access, or CSMA for short. CSMA is a contention-based protocol, and it's also a distributed MAC protocol where nodes make their transmission decisions themselves. This flowchart shows the working of CSMA. When a node has a frame ready for transmission, it performs what is called carrier sensing. You can understand carrier sensing as basically node tries to listen whether there is an ongoing transmission happening, and if that's the case, then it determines that the channel is occupied. In practice, basically nodes would measure the average energy in a channel, and then if that average is larger than threshold, they would conclude that the channel is not idle. Otherwise, they infer that the channel is idle. So if the channel is found to be idle, they transmit the frame. Otherwise, if the channel is not idle, the node will wait and then perform this carrier sensing again. Now, depending on how the nodes wait and how they transmit, there are different subcategories of CSMA. In non-persistent CSMA, a node waits for a random amount of time if it finds channel to be busy. And once the timer expires, it does carrier sensing again. And if again the node finds that the channel is busy, it will just keep doing that again and again. In the case of one persistent CSMA, if a node finds the channel to be occupied, it does not stop doing carrier sensing. It keeps doing that instead, and once the node finds that the channel has become idle, it will transmit its frame. One persistent CSMA was used in classic Ethernet. Then there is P persistent CSMA. It is like one persistent CSMA, except that when the channel becomes free, the transmission is done probabilistically. In one persistent, whenever the channel is free, the node will transmit. In the case of P persistent CSMA, once the channel is free, node will transmit with probability P and defer the transmission to the next slot with probability 1 minus P. Let us say that node starts doing carrier sensing at slot 12 and finds the medium to be busy. Then it does the same for the next slot and the next slot. Now suppose at slot 15 the medium becomes free. Then it will generate a random number. If that number is less than P, it will transmit, otherwise it differs. So suppose the random number that it generated is larger than P, so it differs. It does not transmit in slot 15. again it would do the same thing. Maybe again finds that the number is larger than p, so it does not transmit. Let's say finally in slot 17 it generates a random number, and that is between 0 and p, and therefore it will transmit in slot 17. And from this description should be obvious to you that p persistent CSMA assumes slotted time. So we have this overhead of clock synchronization. The purpose of doing carrier sensing before starting to transmit is to avoid interfering with some ongoing transmission. However, doing carrier sensing does not guarantee that two nodes or more than two nodes will not start transmitting at the same time. And so that's what it's basically mentioned here. So since there is no central control, it is possible for two or nodes to begin transmitting at the same time. And when such a thing happens, the frames basically would interfere with each other, and receiver would not be able to decode the message. And when this happens, the frames are said to have collided, or collision is said to have happened. Although there is something called packet capture, in which even if there is collision, receiver is able to decode the sent message, but that is rare and we are not going to consider that. So we will assume that whenever two or more transmissions occur, we will have collisions. It turns out that in wired networks such as classic Ethernet, a transmitter is able to detect whether there is another ongoing transmission while it is transmitting, which basically means that it can listen and transmit at the same time. And therefore a node is able to detect whether there was a collision or there is a collision ongoing. And in that case, node basically is going to try to retransmit at a later time. And that is referred to as CSMA CD, or stands for CSMA with collision detection. However, in wireless networks, it is not possible to detect collision, because when a node is transmitting, it is usually unable to hear what is going on, because there is a huge discrepancy in transmit and receive powers, could be up to 1,000,000 times. And so therefore in wireless networks, the strategy to deal with collisions is to use ACKs. So when the receiver receives a frame successfully, it will send an ACK, and that would indicate whether a collision happened or not. And that is referred to as CSMA CA, or CSMA with collision avoidance. When collision occurs, whether it is wired or wireless CSMA, nodes wait for a random time interval before attempting retransmission. And when they try to retransmit, they start with carrier sensing once again. And this process of waiting for a random time is called backoff. So the question is, how long should a node wait? And the algorithm that was used in classic Ethernet, and some variant of that is used in modern CSMA implementations, is called exponential backoff, or also called binary exponential backoff, or BEB. In this algorithm, after first collision, a node waits for either 0 or 1 slot chosen randomly. Now this randomization is important. You need to realize that when a collision happens, two or more nodes must be transmitting at the same time. And therefore when they try to retransmit, and we have not used this randomization, they will try to retransmit again at the same time, and they would keep doing it in synchrony, and that's not desirable. If the retransmission was successful, node does not do anything further until a new frame is ready for transmission. If the retransmission was not successful, means there was collision at the second time, then it chooses another time for backoff, and that would be a time slot randomly chosen from the set 0 to through 3, right? So basically we are doubling this window out of which one random number is chosen for backoff. And then again, if the second retransmission was also a collision, then in the next retransmission the window is doubled, and again node is going to choose a random interval starting from 0 slots to 7 slots. And so in general, after ith collision, a node would wait for k time slots where k is chosen uniformly randomly from this set of 0, 1 through 2 to the power I minus 1. Usually this interval doubling would stop after 10 collisions, because then by then the number of slots become large, and so we don't want the node to be waiting for a very long time. Now we shall learn some basic characteristics of wireless links. First, wireless communication supports point to multi-point communication. What it means is that when one node sends, that transmission can be received by multiple nodes. And in some systems, the communication between non-base nodes, right? So typically we would have some special node, right, which we are going to call base station. I will come back to that in some later slide. And then there are other nodes that are called client nodes or non-base nodes. And for example, in Wi-Fi, right, so let's say this node A wants to talk to this node B, right? So they typically don't really communicate directly, although in Wi-Fi they can do so, but usually the way it works is that A communicates to the base station, right, which is called access point in Wi-Fi, and then this base station sends that message to B, something like what we saw in Aloha. As far as wireless links are concerned, people typically use them because they offer mobility, but it does not have to be, and sometimes it's just convenience that we want. We don't want to lay out cables. And so in some systems there's just basically no mobility, right? So neither the base station moves nor the client moves, and that, for example, is the case with WiMAX. The other case, we have limited mobility, so nodes can move as far as they can communicate with the base station, and that's the case with Bluetooth. And then there is another kind where nodes are free to move across different base stations, and that is the case with cellular networks and Wi-Fi. Another characteristic of wireless links is that there exists asymmetry. Usually there exists an asymmetry between capabilities of the two nodes that are connected by a wireless link. And so here is a diagram of a Wi-Fi network where two laptops are connected to a base station, and in Wi-Fi networks these base stations are also called access points or APs, as I said before. Now, these APs are typically powered by power supply, so they are not constrained as far as power is concerned. On the other hand, these devices that connect to AP are powered by battery, and so for them power consumption is an important parameter. And the second is that typically these client nodes are not able to communicate directly with each other, right? So that's another asymmetry. So as I explained before, also to communicate, let's say A wants to communicate to B, A needs to first transmit its frame to the base station, and then this base station would forward it to B. One thing I want to draw your attention to is that we typically draw these wiggly lines. It does not mean that there is a directional transmission or some sort of beam is going on between these two nodes. It's just to indicate that this laptop is connected to this base station. This arrangement where nodes connect to some access point or base station, and this access point routes the frames of the nodes that are connected to it. It's called star topology. There is another arrangement where nodes are all peers and they can communicate either directly or via another node, but the node through which they communicate does not have to be some special node like base station. And these networks are called ad hoc networks, and this topology is called mesh topology. In mesh topology, the messages are forwarded multi-hop by peer nodes. So suppose this node A wants to communicate to this node B, then this message could be first transmitted to this intermediate node, let's call C, and then C may either transmit directly to B or through some other path. And the sort of beauty of this arrangement is that if C for some reason is not able to communicate directly to B, then there are still alternate paths through which it can forward this message to B. One could be sending to let's say D, and then D forwards to B, or there could be another possibility that it takes a longer path through these another two intermediate nodes. And so mesh topology is more robust than star topology. Another characteristic of wireless links is very high bit error rates. Wireless links suffer from much larger bit error rate than wired links, and they may be larger by a factor of 100,000 or more. There are several sources of bit errors that may affect wired links as well, but they affect wireless links much more severely than they affect wired links. And some of them are interference from other ongoing transmissions, then electrical noise coming, for example, from loose wiring, car engines, turning on or off light switches, and so on. Then wireless signals are also absorbed by surroundings, for example, trees, rain, or snow. As we discussed before when we were discussing physical media, that bands, for example, ISM, are particularly susceptible to surroundings that could contain water molecules. Then mobility also introduces errors. There are several models that predict whether a transmission is going to be successful. One such model is called SINR model, or signal to interference plus noise ratio model. According to this model, a receiver can decode a message if the ratio of signal power to interference plus noise power exceeds a given threshold, gamma. So for dealing with high bit rate, to some it may appear that increasing the signal power is the way to go. However, increasing the signal power is usually not a good option because the devices are usually battery powered, and so when we increase the signal power, battery drains faster. And secondly, if we increase the signal power, we are increasing this factor I in neighboring ongoing transmissions, and so basically increase the interference, right? And that's also not good. Even though we might wish to increase the signal power, but maybe because of the regulatory restrictions, that is not an option. And so the methods that we use to deal with high bit rate are: number one, arc. So we use acknowledgements to determine whether the transmission was successful. If not, then basically after a timeout we try again. Second is error correction. As I mentioned in the previous video, this is a method that is heavily used in wireless. And third is a spread spectrum. Basically there are two kinds of methods that we will learn in this video, and that's coming next. Spread spectrum methods are so named because these methods spread the signal over a wider spectrum or frequency band. And this is done to reduce the impact of interference from other devices and to make jamming or interception harder. And these methods originated around World War I, just to defeat the enemy's attempt to jam the ability to communicate. And so there are two kinds of spread spectrum that we are going to study. First is called frequency hopping spread spectrum, or FHSS, and the second one is called direct sequence spread spectrum, or DSSS. The CDMA, or code division multiple access, that is used in 2G and 3G cellular networks, is an instance of direct sequence spread spectrum. Spread spectrum methods rely on pseudo-random number sequences. These sequences are almost random number sequence in the sense that they are generated by some deterministic algorithm, and if we give the same seed, if the initial conditions are the same, then these algorithms generate exactly same random number sequence. And so if the sender and receiver both know the algorithm and they use the same seed, then they will generate the same random number sequence, and that's at the heart of spread spectrum methods. In frequency hopping spread spectrum, nodes transmit signal over a pseudo-random number sequence of frequencies, and the receiver also hops at these frequencies in synchronization with the transmitter. And to maintain synchronization, the receiver and sender would transmit in a particular subband for a given amount of time. So let's suppose that our pseudo-random generator outputs these numbers 313023, and we label our frequency subbands as F0 through F3. Then first the transmission occurs in subband F3, and then it jumps to F1, then again it jumps back to F3, then it jumps to F0 and F2 and F3 and so on. In the case of direct sequence spread spectrum, each bit in the frame is represented by multiple bits in the transmitted signal. So what we do is we generate a pseudo-random number sequence, and we XOR each bit with a fixed number of these random bits that are called chips. and we transmit the XOR of those random bits with the data bits. So here is an example. So suppose our data bits are 1 0 1 0, right? And this is the pseudo random sequence that is generated. So that's 0 1 0 0 and so on. And suppose we use 4 bits as our chips. So basically we have 0 1 0 0, then 1 0 1 1, and then 0 1 0 1, and then 1 0 1 1, right? And again just keeps going. And so what we transmit is the first instance 1 XOR with 0 1 0 0, right? And so that would give us 1 0 1 1, right? So this is what is sent. So 1 0 1 1, right? So this is the first bit. And the second bit is 0, right? And so we XOR with 1 0 1 1, and as a result we send 1 0 1 1 and so on. And these transmitted values are called n-bit chipping code. And again, it's a spread spectrum because we are spreading the signal across a frequency band that is n times wider. Wireless networks is an active area of research, and therefore wireless technologies are constantly evolving. There is a very wide variation in terms of bandwidth and range and other features that different wireless technologies provide. Here is a table that compares 3 technologies: Bluetooth, Wi-Fi, and cellular. In terms of link length, Bluetooth offers about 10 meters and it falls in the category of personal area networks. Wi-Fi covers the order of 100 meters, and this is an instance of local area network. And cellular networks cover tens of kilometers or more, and they are in the category of wide area networks. In terms of data rate, Bluetooth offers up to 2 Mbps, and that is shared up to 7 devices. In the case of Wi-Fi, the latest figure is up to 100 Gbps, and it's shared across all the nodes that are connected to an access point. 3G cellular offered hundreds of kbps, and this rate had been increasing in 5G networks. The data rate is expected to be tens of gigabits per second. Again, according to different features, the uses also vary. Bluetooth is typically used to link a peripheral. Wi-Fi, as I said, it's basically a LAN substitute, so you basically link a computer to a wired base. And 3G cellulars, or more recent ones, are used for making phone calls and also for data connection. The equivalent wired technology is listed in the last row. So equivalent of Bluetooth is USB, equivalent of Wi-Fi is Ethernet, and wired equivalent of 3G is DSL and ISDN. To summarize, medium access control is handled by MAC sublayer, which is the lower part of data link layer. We learned CSMA. CSMA is a widely used medium access control protocol. We learned a few variants of CSMA. We learned non-persistent CSMA, we learned one persistent CSMA, we learned p-persistent CMA. We also saw CSMA CD and CSMA CD. And the thing to remember is that CSMA is a distributed protocol where nodes make the decision to transmit locally. We also saw that wireless transmissions suffer from high bit error rate, and we deal with high bit error rate using mechanisms like ARC and error correction, and we also use spread spectrum. and we learned two spread spectrum methods: frequency hopping spread spectrum and direct sequence spread spectrum. The material covered in this lecture is discussed in detail in Peterson and Devi sections 2.6 through 2.7, and in Tenenbaum and Weatherall's book chapter 4 sections 1 through 3. You might be surprised to know that FHSS was discovered by a film actress. Her name was Hedy Lamarr, and there is a nice Wikipedia article on it, and highly recommend that you read that article. Here is a short quiz for you. Find which of the four statements are correct. You might want to pause this video. I will show the answer in the next slide. The correct answers are B and D. A says Aloha is a contention-free protocol. That's wrong. Aloha is a contention-based protocol. B says CSMA is a distributed protocol where nodes make transmission decisions on their own. That is correct. C says after 4 successive collisions, a node waits for a random interval between 0 and 7 slots if B is used. Remember, after 4 collisions, it's going to wait for a random duration between 0 to 2 to the power I, which is 4 minus 1 slot. So it's going to wait for a random interval between 0 to 15 and not 0 through 7. Fourth, in DSSS, data bits 01 using spreading sequence of 011 00101 are sent as 2-bit chipping code 0101, and that is correct because 0 is going to be XORed with the first 2 bits 01, that gives us 01, and then 1 is going to be XORed with 10, and that gives us 01. So D is also correct. That's all in this video. See you next time.